Hi everyone, let's talk about phase changes or state changes. So we're not talking about a change of state like going to Ohio here. We're talking about a change of state going from solid to liquid to gas, or gas to liquid to solid, or solid to gas, or gas to solid, what have you. Some sort of change of phase or change of state. And it turns out that in addition to seeing the actual physical change that you notice when that occurs, we also have a change in energy. And so the energy that's associated depends on whether you have to add heat or remove heat to make the phase change happen. And whenever you're thinking about that, remember that heat is another term for energy. So we're going to define some phase changes as endothermic or exothermic. Above this table, let me draw in going from solid to liquid to gas. And remember, in order to go from solid to liquid to gas, you need to add energy or add heat, right? If you want to take an ice cube, you need to heat it up to melt it. And so below the table, let me say you're going from gas to liquid to solid. So we're going the other way, gas to liquid to solid. And to do that, you need to remove heat in order to make things get colder and colder and go from gas to liquid to solid. So we have terms for that. You'll notice that melting and vaporization and sublimation, all of these are what I've just labeled in pink, right? They all go solid to liquid to gas. They're all going kind of right on that spectrum that I've just drawn. And you'll notice that they're all also endothermic. And conversely, you'll notice that the other ones, freezing and condensation and deposition, we would all define those as exothermic. And we have this tendency to think of exothermic as warm. And so one question might be like, why is it that we're saying that when you freeze something that's exothermic, it doesn't feel very warm? But it means we are removing heat. So if you remove heat, if you look at this, if you take heat out of whatever you're looking at, that's exothermic, right? You're taking heat out of it. That's why oftentimes reactions feel warm. But if you remove heat from something, then you go gradually from gas to liquid to solid. You get kind of colder as you go along. So that's why those are exothermic, whereas endothermic means we're adding heat, we're absorbing heat from the surroundings. Let's also talk about the process of vaporization. So specifically, vaporization is the liquid to gas phase change. And a question that often comes up is if you take a shower, right, you'll notice that if it's a long shower and it's warm, you might look in the mirror when you're done and the mirror has all of this liquid on it, right? It's really foggy. But we know something. We know that the boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. And I don't know about you, but I'm not trying to stick my hand in a pot of boiling water. So how is it that you are taking a shower and not burning yourself, and therefore you're not boiling water, but yet you have gaseous water making its way over to the mirror? What's going on there? Well, it turns out there's a difference between boiling and evaporation. So boiling takes place throughout an entire liquid. You'll notice in this picture here, the boiling is always starting at the bottom. And typically if you boil a pot of water, the bubbles begin at the bottom because that's where the most heat is on your stove. Whereas evaporation is the ability of molecules only at the surface to change from the liquid state to the gaseous state. And then oftentimes they'll re-enter, which we talk about in a second. But it turns out that evaporation can happen where just a few surface molecules get enough energy to get transmitted out of the liquid phase and into the gaseous phase. So that's what's going on in your bathroom when you have a shower and the condensation ends up on your mirror. We have evaporation going on, not boiling. We have just a few molecules that get enough energy to jump into the gaseous stage. And you've seen this, right? You've seen puddles disappear, and puddles typically disappear more quickly if they're under sunshine when they're getting extra energy so they can evaporate more quickly. But they're not boiling. It's not 212 degrees outside for sure. Let's talk about that kind of intersection between molecules leaving the liquid phase and going into the gas phase and then re-entering the liquid phase. So we have this constant kind of battle between molecules that you see here that get enough energy to jump into the gaseous phase, which is up here, but then it turns out some of them lose energy as gases and they return down to the liquid phase over here on the right-hand side. And so over time, that kind of back and forth continues, and we call that equilibrium. So we've reached a liquid vapor equilibrium in a system when the rate of molecules leaving the liquid to turn into gas equals the rate of the molecules leaving the gas to turn back into liquid. And that's what you see here. We have molecules both going from gas to liquid and liquid to gas kind of at the same rate. So we have achieved a liquid vapor equilibrium. And so if you just start out a process very early, most of the molecules are going to be in a liquid, but then as you let it sit for a while, you'll have a whole lot of stuff in the gaseous phase, and eventually those things need to equal out, kind of like diffusion. If you think about lowering a concentration gradient, that's what we're doing here, except the concentration is really number of particles in the gas phase. And so when we're thinking about equilibrium, we care about trying to get kind of a balance between what we have in the gas phase and what we have in the liquid phase. Now, there is a pressure associated with that. So something called the equilibrium vapor pressure is defined as the pressure within that liquid that allows you to have molecules escape to the gaseous phase. And one of the coolest applications of that is boiling point. So when we're thinking about a boiling point, it turns out that boiling is defined as when the pressure of your liquid, and I'm going to call that your vapor pressure, so your pressure of your vapor becomes greater than the pressure of the atmosphere pushing down. So we have this constant kind of battle. Let's imagine you're boiling a pot of water. So here is your nice pot of water, and you have water in here, and there is a pressure in this water called the vapor pressure, and that increases as you increase the temperature. And there's also atmospheric pressure pushing down. So all of the gas molecules are pushing down on the surface of your liquid. That's your atmospheric pressure. As soon as your vapor pressure gets large enough to overcome atmospheric pressure pushing down, some of these molecules start to go away, and that is what we know as boiling. And it turns out that at high elevations, for instance, like in Denver, if you're going camping in the mountains, atmospheric pressure is less because you're at a higher elevation, so there's less gas molecules pushing down on you. And so if atmospheric pressure is less, that means it's easier for you to boil water. But there's a catch, right? So it's easier for you to get the vapor pressure to overcome atmospheric pressure. But if it's easier to do that, that means it boils at a lower temperature. So just hypothetically, let's imagine that the new boiling point of water at a high elevation in the mountains is something like 90 degrees Celsius instead of 100. Then, when you're trying to do something like cook your pasta in the mountains, you have to boil that pasta for a lot longer because it is boiling and cooking at a lower temperature. And this is actually noticeable. If you're out in the mountains, even at a relatively low elevation, like maybe between 5 and 10,000 feet, so we're not talking about Mount Everest here, there's a noticeable difference in the amount of time it takes you to cook food because the vapor pressure within your liquid you can't get your liquid hotter than 90 degrees because as soon as it gets hotter than 90 degrees, it turns into steam and is no longer in your pot. So it's impossible for you to cook stuff in water at a higher temperature. So it's kind of a cool application of this idea of equilibrium vapor pressure and in particular boiling point.